Good afternoon, everyone, all the participants to day 5 of the Atal LDP today, and it is my great honor to welcome our esteemed resource person today. And before I read out his eminency through his profile, I would first of all request Dr. O.P. Singh sir to please felicitate our resource person, Professor B.S. Daya Sagar, in a traditional Sikkimese way by offering him khada and a memento of Sikkim Manipal Institute of Technology. Thank you very much. I take the opportunity to read out the profile of Professor B.S. Daya Sagar, who is a professor of the Systems Science and Informatics Unit and head of the Indian Statistical Institute, Bangalore Center. Professor Sagar received his MSc and PhD degrees in Geoengineering and Remote Sensing from the Faculty of Engineering, Andhra Pradesh, Andhra University, Visakhapatnam, India in 1991 and 1994 respectively. He is also the founding head of the SSIU. Earlier, he worked in the College of Engineering, Andhra University and the Center for Remote Imaging, Sensing and Processing, the National University of Singapore, in various positions from 1992 to 2001. He served as Associate Professor and Researcher in the Faculty of Engineering and Technology, Multimedia University, Malaysia, from 2001 to 2007. Professor Sagar has made significant contributions to geosciences with particular emphasis on developing spatial algorithms meant for geopattern retrieval, analysis, reasoning, modeling, and visualization by using mathematical morphology and fractal geometry concepts. He has published over 90 papers in journals and has authored and guest edited 14 books and spatial theme issues for journals. He authored a book entitled Mathematical Morphology in Geomorphology and GISI in CRC Press, Boca Raton, 2013. He co-edited 2 spatial issues on filtering and segmentation with mathematical morphology of IEEE Journal of Selected Topics in Signal Processing and Applied Earth Observation and Remote Sensing in India for IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing. His book, Handbook of Mathematical Geosciences in Springer Publishers, crossed 1.23 million downloads. His 2-volume Encyclopedia of Mathematical Geosciences, Springer Nature, is released in 2023. He was elected as a member of the New York Academy of Sciences in 1995, as a Fellow of the Royal Geographical Society in 2000, as a Senior Member of IEEE Geoscience and Remote Sensing Society in 2003, as a Fellow of the Indian Geophysical Union in 2011, as a Fellow of the Indian Academy of Sciences in 2022, and the Indian National Science Academy in 2024. He has also been a member of the American Geophysical Union since 2004 and a life member of the International Association for Mathematical Geosciences. He delivered the Curzon and Company Seschachalam Lecture 2009 at Sharada Ranganathan Endowment Lectures, Bangalore, and the Frank Harare Endowment Lecture 2019 at International Conference on Discrete Mathematics 2019. He was awarded the Dr. Balakrishna Memorial Award of the Andhra Pradesh Academy of Sciences in 1995, the Krishnan Medal of the Indian Geophysical Union in 2002, the Georges Mathuran Award 2011 with lecturership of the IAMG, and the award of IAMG Certificate of Appreciation in 2018. He is the founding chairman of the Bangalore section IEEE GRSS chapter. He has been appointed as an IEEE Geoscience and Remote Sensing Society Distinguished Lecturer for 3 years from 2020 to 2024. He is an AJU Honors and Recognition Committee member. He is on the editorial boards of Computers and Geosciences Frontiers environmental informatics and mathematical geosciences. I welcome you, sir, and this is over to you. The stage is over to you. Thank you.
And this is not inside, it is wrong. So is there any point? No problem. I'll speak from here. Yeah, so good evening everyone. And sorry that many things have happened for the last 1 week. And initially I said I have to cancel my trip to Sikkim, but both of them they did not organize, they did not leave me. So, delighted to be here. And this topic is also very interesting, and this FDP topic of artificial intelligence and remote sensing is, now many people are working on these areas. But to be frank, I know nothing about AI, but mathematical morphology is a nice AI tool. And there is a person by name Professor Isabella Bloch, and she has written a wonderful tutorial on how mathematical morphology is a wonderful artificial intelligence tool. And you have to look at that tutorial. I'll mention later on, probably I'll put it on, so I can write it on this board, her name? Yes. Yeah, so, anyway, so we'll see that. Her name is, you can just type and see, Isabella Bloch. She is a French professor. She works for, I think she works for École Polytechnique, Paris. And she has written a nice tutorial how mathematical morphology offers numerous AI-like transformations and things, right? So, remote sensing and earth observation is the main focus. And one was Swalpa Roy was here, and he has been doing a lot of things on deep learning, machine learning, and the right words he has been using, and mostly for classification of hyperspectral remotely sensed data. But my work is mostly on development of morphology-based algorithms for various different purposes. One major emphasis is on digital elevation models. I think if you are quite familiar with remote sensing, satellite remote sensing, I am also sure that you will be knowing digital elevation models. DEMs are not as colorful as hyperspectral images, but it has a very rich geometric, morphologic and topologic information. It is not visible outwardly, but if you have a kind of geometrically relevant mathematics knowledge, and you can unravel many hidden features, many features that are hidden to our naked eye from digital elevation models. I always used to tell that DEMs were heavily used, mostly as the inputs in commercial softwares, and whatever commercial software gives as an output, we are quite convinced. But are those the only routines that we have with commercial software sufficient for us? I feel that there is lot of science outcome that you can derive from digital elevation models. I was talking to, on my way from guest house with Aranya, she was talking about wildlife oriented on that. Corridors. Wildlife actually move through corridors, natural corridors. And when I was reading the works of Isabella Bloch, she works on robot path planning and all that. How a robot can take one point to another point, and which is the shortest path and how it moves and all that. In that process, she has also proposed many things about what is the between space. Given two objects, let us say both objects are convex objects, and computing the between space is not too difficult. Between space in the sense, let us say there is one object, this is my left hand and right hand. The between space is the space, this is the between space. She says it is a betweenness. And suppose these objects are like concave like this, still you can compute the betweenness. Suppose it is like this and it is like this, betweenness will be a problem. Or if it is like this. And you get, other than betweenness also, you get some other features. But typically how to compute a betweenness has a role to play in computing the natural corridors. So as I was seeing the beautiful, nature like the Tista river is flowing, and the two rivers were parallelly running. And typically the space in between these two big hill ranges, this is the corridor. Those corridors, we know how to mark those things by looking at the satellite images, but can we do that in automated way? It is possible, and it is possible with morphology. So, but it is not there as a case study, but when she was talking, and then when the focus is on mostly on Earth observation and remote sensing and digital elevation models, in DEMs you don't see any other features. You will see only elevations. And so higher elevation zones are with very bright pixels, and then lowest elevations are with the darkest pixels. In between you have so many different shades, right? So, but it's also an image. Probably it's a main byproduct from the remotely sensed satellite data. So that byproduct, to generate digital elevation models, billions of dollars were spent, but it is not being fully utilized. And so this was, I was arguing with Dr. Paul Rosen, who was the team leader for shuttle radar topographic mission. SRTM or DEMs are very famous. And he was the team leader, and he also is now leader for the NISAR mission, NASA ISRO centric aperture radar mission, now which is to be launched very soon. And when I mentioned that, no, don't say that, and we know that billions of dollars spent, but I said it is not being fully utilized. Because many people, what they do, they take a commercial software and then they use it very nicely for watershed modeling, because it gives nice river networks and ridge connectivity networks, and it can partition the watersheds and all that. But will those routines work for all regions? And so very hilly regions and very flat regions like tidal regions. Many of those routines which are very successful at the hilly regions are failures at flat regions, because they use a simple Newton's descent property, and then they start computing these river networks and all that. So, but morphology has a different kind of way. It doesn't consider simple spectral values. It considers geometric aspects of the images, as the image that I emphasize here is digital elevation models, right? So as I also mentioned, it is an illustrative overview, and I will skip most of the math because I think I have to give 1 hour, 90 minutes. 90 minutes. So I will, but I will just give you a glimpse of mathematical morphology. It is really worth spending time learning mathematical morphology. It is not too difficult mathematics. So I am a non-mathematician, but I could learn mathematical morphology. And it is, if you are familiar with a bit of perceptive knowledge, that will be fairly sufficient to venture into mathematical morphology. And of course, there are many pure mathematicians, they did a lot of work, and then but they are more of a lattice theory and theoretical aspects. But I don't do that kind of research. So whenever you take a system, I would call that, from the physics point of view, dynamical systems or data sciences. Now data sciences, I would say 4 or 5 major ingredients. One is data acquisition, assuming that the data that you have acquired or data that you have access with is very precise. And next, what do we really do with that? We will try to retrieve information from that. That information is from person to person, it changes. I have a lot of interest in extraction of the water bodies from the satellite data. That is my information. And many of you are having a different kind of interest. Like some people, they look at plant types and vegetation phenology, and some people they look at hydrological phenomena. Some people they look at, as I mentioned, some natural corridors, and some people they look at where are the geological lineaments, and it all depends on the user's interest. Sorry, I have not asked and what are your backgrounds because it takes time, but just take it and then we can always discuss, and we can have a full-length mathematical morphology workshop. And so 2 weeks workshop I have organized several times, and at DST summer schools, and we will plan for that. But this is only to just impress you with, there is a field called mathematical morphology, but that mathematical morphology would really, I used to tell, take it to heart and then think everything through morphology, and you have a different kind of original ideas, right? So the 4 or 5 ingredients are information retrieval, information analysis, and information reasoning, visualization and modeling. So for all this, and I realize that mathematical morphology has a role to play in all these 4 or 5 ingredients. And how I have used mathematical morphology for a retrieval of information, that information that I have interested in is mostly the unique topological networks. Unique topological networks in geological sense is a river network. So in mathematical morphology there is a transformation called skeletonization, and given in any object or any function, spatial function, and the skeletonization will convert them into skeletons. Given the outline of my body, and so that skeletonization will find out the whole skeletal network of my body. It's a nice thing, like given an object, and if I ask you convert that as a 1 pixel wide caricature which summarizes overall shape, size and orientation of the particular object. So it does that operation. So it has a motivation. If you take a ribbon skeleton is a medial axis, a thin line in between these 2 outlines. Or you have a road and the divider is typically the skeleton. So such skeletons are actually on terrestrial surface of the river networks. I would say river network is the skeleton of the whole terrestrial surface. Can I reconstruct the whole terrestrial surface from the river network? typically it should be possible. Like when my whole body is converted as a skeleton, and from skeleton the whole body can be constructed. It has many computer science applications also. Earlier, coding of binary images through skeletonization, because that coding would get you an option to transmit an object after it is converted to a skeleton, which occupies much lesser space. Assume that an object occupies about 200 pixels. The moment you convert that into its skeleton, it may occupy just 15 or 16 pixels. So transmit that skeleton, and then if you know how you have converted the object into skeleton, and you can reconstruct that, and then you can tell that many in electrical electronics engineering, in image processing, alias coding, Huffman codings are very popular. But the skeletonization based coding is also very popular, and which was very nicely explained by Petros Margos. And so that was the original application. But I have used that skeletonization for something else, and I used to see digital elevation models. So this was about 35 years ago, and my supervisor used to tell, and you mark all geophysically relevant features by looking at left side, right side aerial photographs, putting a stereoscope. And people used to say that, oh, I am able to see all mountains are hitting my eyes, valleys are very deep, depressed, but I never felt, I don't have that stereoscopic view, and I had very high eyesight. But I used to bully my Guruji. Yeah, I am able to see, but I never used to see. But that was, anyway, but I have to pass and I have to clear my coursework. I used to tell him, oh, you used to see, and then he revealed once, I never used to see, people are telling everybody is seeing. My Guruji was actually from IIT Kharagpur, exploration geophysics professor. I think, sir, you have also very high eyesight, and I also have very high eyesight. That is the reason we don't. You said you are seeing, and then I revealed that no, I didn't see, sir. By that time I was already graduated. No. So, but I was actually looking at these digital elevation models. It has, you can see that a kind of skeletal-like pattern. It is not exactly the skeleton. But when you see those shades, like very bright shade to darker shades, and you feel that there is a kind of structure. You can see those images. I will show subsequently. Yeah. So typically this is the one, and this is the one which I have shown is a synthetic digital elevation model. You can see that very bright regions are there. There is a potential skeletal-like feature is there, which is obvious to our naked eyes, but how to extract that? So when you have very large scale data sets and you require the complete computational powers you have to use, and you cannot put a tracing sheet and mark. If it is for a small prototype study, you can always do that. So to extract that and how we use the skeletonization, that is one aspect. And this the second line I always show is the digital elevation model is an engineering marvel. So it uses the principle of simple parallax, and when you put left side and right side images, try to register, and it gets registered, but it doesn't get registered accurately, precisely, and there is a slight amount of distortion. That based on that parallax computations, and then they compute the elevations of 3D structures of the given objects. And but as I mentioned, which is a very important source of data for both geoscientists and planetary geoscientists. Now Chandrayaan DEMs, I don't know whether you people have seen, particularly Chandrayaan 2 has a specific sensor called OHRC, optical high resolution camera. That OHRC based images are very high resolution. You can see a pebble of 25 centimeters. So small rocks also you can see that. And then DEMs generated from OHRC data, I believe they have not given it to public, but they are still keeping with themselves. But it is very high resolution. Then I felt that we are not lagging behind any developed country. We are on par with them, if not better than them. So these DEMs are really interesting. And as I mentioned, planetary geoscientists, they have, because on moon surface, those DEMs are very interesting to see. There are so many, degraded craters. And what is the degree of degradation? And is it a recent phenomenon or millions of years back it has happened? They actually look at that rim of that erupted volcano. They are not actually volcanoes, impact craters. Some meteorites used to hit and then those impact craters happen. And there is that rim actually tells the age of those impact craters. And to study those things, or one mathematical field, if you are thorough with it, if you are able to think through that mathematical field, you enjoy both research and then you also get very interesting features that nobody has really shown so far, right? So mathematical morphology is an area of geoscience that most people don't realize will literally change the way they look at Earth. I will fully agree with this. This was actually written for me by Dr. Paul Rosen, and he nominated me once for some fellowship, and then he understood that, oh, mathematical morphology is all about this, and you spent almost 3 decades in it, and then let me write. So I think through mostly morphological aspects of the given data set. So when I teach my students, information science students in ISI, Indian Statistical Institute, and they don't have interest on this remote sensing and Earth observation. They have interest on any general data. So general data is, I can tell that demographic data, population distribution, population density, grid cell wise. If you have such kind of data, treat that data as a kind of relief. Where there is a high population density, show that as a high reflectance value, grayscale value. Where there is no population density, and you just show that as 0 value. And then when you represent that as a kind of surface, it's a kind of landscape. So like demographic landscape and retrieval of these unique features are like the skeletons. The dual of the skeleton is, as I mentioned, skeleton is a river network. Dual of the river network is ridge networks. So this is typically like this. These are the 2 ridges. You have a valley path here and stream flows here. And each stream segment is surrounded by, embedded between 2 ridge lines. If you look at topographic maps and you don't see ridge lines, you see only blue lines. Blue lines are river networks. But those ridge and valleys have some kind of dual relationships. And you have a DEM, and from DEM I can extract the river network. And if I invert the DEM, and if I use the same transformation which I used to extract the river network, and I get not the river network, but its dual, that is the ridge connectivity network. It's just a matter of mindset to understand what is terrestrial surface. If someone asks me to tell in just 2 or 3 words, and I say there is a surface, there are 2 unique connectivity networks. One is valley connectivity network, another one is ridge connectivity network. In between you have all hill slopes. It is as simple as that. But it gives a lot of rich scientific outcomes if we really pay attention through some mathematics, as I mentioned, because mathematical morphology is very familiar to me, and then I am using that. But there are several people who are experts in fractal geometry, discrete mathematics, wavelet theory, fuzzy set theory, and then there are many similarities, rough set theory across mathematical morphology and this kind of contemporary modern tools, right? So in entire mathematical morphology, data will be investigated with another data. That is the last statement. You have data,